This is the National Science Society of Black Physicists Big Science Hour. This is the second Big Science Hour. And this time around, we're going to be focusing on fusion science. As I mentioned earlier, fusion is, of course, very important. In the very near future, we need new sources of energy. And specifically, fusion science offers the possibility of harnessing nuclear fusion in order to provide for our energy needs. That said, we have a wonderful group of speakers that's going to tell us about the most recent developments in fusion science. And this particular session is moderated by my good friend, Dr. Sakazi Mtingwa. And Dr. Sakazi has a wealth of experience, and he put together this panel. And without further ado, Dr. Sakazi.
Thank you. I appreciate that. Thank you so much for the introduction, Carol. So we today will be hearing about advances in fusion and plasma physics. For decades, people have been trying to fuse these nuclei together to create energy for electricity and other purposes. And it's always been 10 years. It never seems to quite get there, but there have been some major breakthroughs that have happened within the last year, actually. And so we wanted to bring that to you. So we have three speakers. We have Professor Ed Thomas from Auburn University. He will be the first speaker, and he will be talking about advances in fusion, space, low temperature plasma science in general. Professor Thomas received a bachelor's degree from Florida Institute of Technology, master's in physics from MIT, went on to get his PhD from Auburn University. He began his research career in experimental studies of edge particle transport in fusion plasmas, which has expanded into experimental and computational investigations of dusty plasmas, strongly magnetized plasmas, and laboratory simulations of the space environment. Professor Thomas was elected member of the International Union of Radio Sciences Commission H. He is an APS fellow. More importantly, he is an NSBP fellow. He served on numerous advisory committees for the American Physical Society, National Science Foundation, Department of Energy, the National Academies, and the European Space Agency. And he's currently serving as the chair-elect of the American Physical Society's Division of Plasma Physics. And without further ado, I present to you Professor Ed Thomas.
Great. Thank you, Sakazi. Sakazi is someone I've known for many years. We won't go back how long, because no, we won't. So this is a really wonderful opportunity, and particularly for the students in the audience. There's a sequence of three talks. I'm giving the first one. Connie Williams, who's a PhD student, is giving the second one. Ronnie Shepard is giving the third one. As we talked about it, I'm going to give my talk not so much focused on my own group's research, but really to give an introduction to plasma physics and plasma science. And I hope with this brief introduction, I can convey the real excitement that I have and all of us working in plasma science have for this field. This is an example of something called a dusty plasma. This is something that is in my laboratory. It actually is in the form of a torus, which is particularly relevant because that's the configuration you use for fusion experiments. This work that we do in our laboratory is supported by the Department of Energy, the NSF, NASA, and in particular, I want to highlight our collaborative user facility, which is the Magnetized Plasma Research Lab, which is funded by DOE, and I'm co-PI of a statewide EPSCoR center, the Future Technologies Enabled by Plasma Processes, which is on low temperature plasmas in the state of Alabama. So the question about plasmas is, where do plasmas sit? Plasma physics is this area that's honestly not well represented in this community. And so I always like to start when I have an opportunity to talk about plasmas to describe where do plasmas actually sit in the grand scheme of physics. So I'm a professor, so I will walk around and I will talk and I'll move my hands. So physics, this is Sir Isaac, and most of Newtonian physics is basically objects that are about, this big, moving at about this pace. And we've kind of described physics as it's evolved in many different ways. We first of all introduced this idea that you can have objects that move very fast. and that's the realm of special relativity. We also have objects that can get very big, very massive, so that's general relativity. And those are all extensions of Newtonian physics. You can also have objects that are very small, and that's the realm of quantum mechanics. And now you can have connections between these. For example, you can connect the very fast and the very big, and that's kind of your area of astrophysics and cosmology. You can also connect the very small and the very fast, and that's where particle physics lies. And then you can actually connect the very small to the very big, and that's where your theories of quantum gravity sit. But plasma physics is not any of those. I would argue that plasma physics sits in a completely different branch. And that branch is the very complex. This is where you have, if you take any pair of objects, the interactions are extremely simple to describe. I have two charged objects. I can describe them by Coulomb's law, except that I have 100 trillion of those interactions that I have to solve simultaneously, and that's where the problem comes from. And this is where the very complex involves weather and fluids and plasmas. And this is where I think plasma physics sits. So many of you have probably seen these images. Plasmas evolve from solids to liquids to gases. Plasmas are these ionized states of matter. And in every plasma physics talk, we are legally bound to show this figure, which shows temperature on one axis, density on the other axis, to say everything that's boring in the universe is the solids, liquids, and gases at cold temperatures, high densities, and we do the cool stuff, which is all up here at high temperature and moderate densities. But we are legally bound to show this figure. Every plasma physics talk you will ever see will show that figure. But realistically, what do we mean by a plasma? Where do plasmas sit in the grand scheme of physics? We are at the intersection between electromagnetism and statistical mechanics and classical mechanics. And this is the realm where plasmas live. We are looking at having charged particles interacting via Coulomb interactions or screened Coulomb forces. You have large numbers of interactions, as I indicated. Those long-range interactions, because you are interacting through electromagnetic fields, those lead to collective behavior and resulting self-organization. And it's that collective behavior and the self-organization of a plasma that kind of distinguishes it from the other states of matter. And therefore, you have a realm of scientifically rich problems that are going to be governed by non-equilibrium processes and by nonlinear dynamics. And that's kind of what, for us, makes a plasma a scientifically rich system. So where do we find plasmas? What kinds of physical systems are involved in plasmas? Well, plasmas exist from nanometer scale to light years. We cover a massive range of parameter space. Plasmas are involved in human-made activities from plasma manufacturing, plasma medicine, plasma agriculture. That image there, that's not a Photoshop. You can now take a low temperature plasma and let it interact with your hand. And we actually make those in my lab, and that's actually really cool. You have laboratory experiments, and a big part of what I'm going to focus on today is fusion energy. But plasmas occur in a wide range of naturally occurring environments, from lightning, the sun-Earth connection, this is the so-called space weather problem, astrophysical jets, which power black holes, or powered by black holes, and then the entire process of star and planet formation involves charged plasma, or plasma, charged dust, and interactions with each other. We're talking massive scale differences from tens of meters to light years, and this is where plasmas sit. And I had the good fortune of serving on the decadal review of plasma science in 2020, a report that we generated called Plasma 2020. And I'm not going to read the whole thing, but basically the idea here is that advances in plasma science are critical to our technological development, and they impact everything from materials to healthcare to space weather. And of course, buried in all of that is fusion. And if you get a chance to read it, if you love reading national reports, which I'm sure everybody does, it's actually a really well written, and I'm not just saying that because I helped write part of it, but it's actually a well written report. So with that as a very brief introduction to what plasma science is, what plasmas can do for you, I want to highlight picking just a couple of examples from different areas of plasma science, and to tell you a little bit about where plasma science is going and some of the really amazing things that have been advanced in the last, just even the last 2 or 3 years. The first, I'm going to talk about fusion energy, some work in space and astrophysical plasmas, and then work in low temperature plasmas, which is where I do most of my work these days. So what is fusion? Fusion is basically the power source of stars. What we are trying to do in the fusion community is literally to make a star on Earth. And this, there's probably no greater grand challenge than trying to recreate a star in a magnetic bottle on Earth. And so what is involved in this? So the core of what we try to do in most fusion experiments is to take an isotope of hydrogen, deuterium, another one, tritium, combine them together under the right conditions, produce an alpha particle, which is a helium nucleus, and a neutron, which is carrying 14.1 MeV. Now, this is not the only path to fusion. There are many paths to fusion. But the reason that many fusion scientists like this one, this is a measure of cross-section. You can basically think of this as the probability, if you get the conditions right, of fusion occurring. And you'll see that this is your DT reaction, and this one has the highest peak at somewhere in the neighborhood of 300 or 400 million degrees. So all you've got to do is get matter up to a few 100 million degrees, and you got this. This is not a problem, right? So what do? We actually are getting very close to making those conditions on Earth. Okay, so the basic way we try to do this, you've got matter that is at hundreds of millions of degrees. We got to be able to confine it because you don't want that matter interacting with a physical piece of metal that's going to be holding this. And so the general approach of magnetic fusion, which is what I'm going to discuss first, is to basically build a magnetic bottle that can hold this very, very hot plasma. We do this in a couple of different ways. One geometry is called a tokamak, which was invented in Russia. The other one is called stellarator, which was originally invented in the US. They basically operate by having a set of magnetic field coils that surround a vacuum chamber. You heat up the plasma on the inside, and this magnetic bottle, a combination of magnetic fields that go the long way and the short way around the machine, will be able to hold this hot plasma together. Tokamaks and stellarators are the two leading configurations for magnetic fusion. There are others. This morning we heard a really lovely talk by the folks from TAE, or a pair of talks from TAE on using another configuration called a field reverse configuration. So this is not unique, but these are the ones that have achieved the best fusion conditions so far. A stellarator is confusing because it has to use it produces a three-dimensional magnetic field. To give you a sense of what the bay looks like, this is the world's largest stellarator in Germany called Wendelstein 7X. The big mixy thing with all the coils is buried someplace underneath all of this stuff. But Wendelstein is actually an operating machine. It actually just began its phase 4, phase 5 of operations in the last couple of months. The other configuration is called the tokamak, and this is the design of the world's largest tokamak. To give you a sense of scale, there is a person right about there. And ITER is going to be, in the previous talk, you actually heard mention about ITER. ITER is currently under construction. And in fact, a major milestone occurred in May of 2022. This was the first section of ITER being lowered in place on its central stack. And so ITER is actually now being assembled. It's no longer just a purely theoretical concept like it had been for 20 years, but it's actually being built. And we expect it to actually be assembled over the next 2 to 3 years and begin plasma operations in the 25-26 period. But that's not the only major milestone. In the last couple of years, there's actually been a real big burst of public-private partnerships in fusion. The aforementioned TAE is one of those. Another big one is a company called Commonwealth Fusion Systems that, as I said, you have to make a very good magnetic bottle. And the better the magnetic bottle, the more power density you can have, and you can raise the temperature inside of your fusion experiment to higher and higher temperatures. The record so far was a device at MIT roughly producing about 8 Tesla at the center. Spark is using a new design of a superconducting magnet, and they did a full-scale test this past September, producing 20 Tesla in a superconducting coil, which is absolutely remarkable since the energy density should scale like B squared. So if you're going from 8 Tesla to 20 Tesla, you're taking that and you're squaring that. That's a really big deal. The Joint European Torus in December of last year actually used deuterium and tritium and produced a record fusion output power of 59 megajoules of stored energy over 5 seconds. So a really good burn, well, not burn, but a really good plasma performance, producing net fusion power over a few seconds. And then to top it off, a few weeks later, the East tokamak in Hefei, China, which was a superconducting tokamak, produced a high performance plasma at about 90 million Kelvin for over 1,000 seconds. Now, yes, none of them have achieved fusion yet in a sustained way, but we're moving in the way there. When I got started, having a plasma that could be sustained under fusion conditions for milliseconds would have been considered amazing. We're now up to seconds and hundreds of seconds and thousands of seconds for high performance plasmas. This is really, really remarkable. But what's even more remarkable is what my 2 following speakers are going to talk about, because there's another path to fusion, which is not magnetic. It's actually called inertial confinement fusion. This is basically taking a whole lot of laser beams, picking a fuel target, and blasting the crap out of it until the gas gives up and starts burning. And in fact, in August of 2021, they achieved something that the magnetic fusion community said, you can't do it. They actually ignited a plasma. The plasma was producing net power for a short period of time. I'll let those guys explain it. But the next 2 talks are going to talk about laser fusion. And this result, the entire plasma community was absolutely amazed by it. It was achieved on a facility called the National Ignition Facility, and it achieved its mission of igniting a plasma. And that is, in this grand scheme of human science and plasma science, for a brief moment in time, we made a star. And that was really cool. Okay. So beyond looking at fusion, there is also an enormous amount of work in plasma physics. As I said, it encompasses many, many different fields. I've had the very good fortune of working in fusion and in space plasmas and in low temperature plasmas. And having this opportunity, I'd be remiss if I didn't point out the other areas that I actually where I do most of my work now, which is in astrophysical space plasmas and low temperature plasmas. In space plasmas, that basically means looking at the plasma environment outside of the surface of the Earth, basically starting at about 100 kilometers above the surface of the Earth, all the way out into the rest of the solar system, you're dominated by plasmas, okay? Everything below about 50 kilometers is either a solid, liquid, or gas. 50 to 100 is a transition region, and everything above 100, you're in the realm of plasma physics. And NASA has an entire fleet, and not just NASA, many other countries have an entire fleet of satellites trying to understand space weather. Here's the sun, This little light purple region is the magnetic bubble created by the Earth's magnetic field. And then this is the bow shock, where the sun's plasma, which is supersonic relative to the magnetic field region around the Earth, goes through a shock, and then waves off of that shock front move in towards the Earth, creating space weather. And there's a whole fleet of satellites trying to understand that. But not only that, we can actually perform laboratory experiments here on Earth to understand some of the physical properties of that space plasma environment. I'll show you two. One is from about 10 years ago. This is one of my former PhD students, Amy Dubois, actually looking at the generation of a variety of waves that you would see generated in the downstream bow shock, the downstream plasma, here where you've got the solar plasma compressing the magnetic field structure beyond the Earth and generating waves. And what Amy's PhD did was to actually show and prove a theory by our colleague Guru Ganguly that by changing the amount of compression that you get on the backside, you can actually make a transition from one type of wave, which is called Kelvin-Helmholtz, to another one called ion cyclotron, to another one called electrostatic ion hybrid. And Amy was the first person to actually prove that you could make that measurement in the laboratory. And this was done in one of our linear machines. The big brother of one of these linear machines is a device at UCLA. Again, for scale, my machine's about 1.5 meters, 2 meters long. This one is 20 meters long. And they actually did a really remarkable experiment, actually trying to understand the physics of the auroral formation. So this is just a photo of the aurora. And they did an experiment using a very, very long wavelength wave in a plasma called an Alfvén wave, and proving in the laboratory that the electron acceleration by these Alfvén waves can be a mechanism that can power the aurora. And so these are the kinds of things that laboratory physicists like myself do in connection to space plasmas and allow us to study fundamental phenomena in the laboratory. Now, one of the grand challenges in space plasmas is to actually understand how the Earth and Sun are connected to each other. One of the greatest grand challenges in all of space physics, the surface of the Sun is about 5,600 Kelvin. The corona in the environment above the Sun is at about 1,000,000 Kelvin. The further away you move from the Sun for a short period of time, things get hotter. And trying to understand that has been a grand challenge of plasma physics for decades. And then that solar corona evolves outward and extends out from the Sun and becomes the solar wind. And we want to figure out what the origin of magnetic structure in the solar wind is. And right now, you've probably heard of Parker Solar Probe. Parker Solar Probe is a probe launched from Earth several years ago. It's actually flying towards the Sun. That's the Milky Way. And you're seeing streamers of energetic particles and the plasma near the Sun as Parker actually flies in and literally touches the surface of the Sun. And there are a whole variety of theories that are trying to understand where some of the magnetic structure comes from. I'll just point out one of these, the top one here, reconnecting field lines. That's actually the PI of this FTPP project, Gary Zank from the University of Alabama at Huntsville, the correct one, this is actually his theory as one of these mechanisms for how this works. And finally, again, as a plasma physicist, we all were really super, super excited. Oh my goodness, we've made images of a black hole. Now, the plasma physicists were a little annoyed because, okay, yeah, you can't actually see the black hole. You see all the stuff going around it. And come on, NASA, just say the words. What you're actually seeing is the plasma, or can we say it? We're seeing the plasma around the black hole, and that's what's actually your imaging. So yes, we give all props to the Event Horizon Telescope, but what you're actually seeing is the plasma. And what's actually really cool is that if you're using EHT, they've actually been able to study the origins of astrophysical jets by looking at how these jets emerge from the central black hole. But let's keep in mind, you're not seeing the black hole, you're seeing the plasma around the black hole. Okay, so finally, in the last few slides, we'll just talk a little bit about low temperature plasmas and my own work. Low temperature plasmas are perhaps one of the greatest, yet also most under-recognized parts of the plasma science community. This was an article that I helped contribute to, the 2022 Plasma Roadmap, and these are all the different topics that scientists around the world all contributed to in this roadmap. Some of the things that we highlighted: plasma waste-to-energy systems, plasma-based thrusters, and in fact, a lot of work that was done in the last 2 years on using plasmas to sterilize the COVID-19 virus. But more than that, and if you don't take anything else away from this talk, the technologies enabled by plasmas, as reported that we looked up in when we were doing Plasma 2020, contribute to between $0.5 and $2 trillion with a T dollars per year to the worldwide economy. And that is what plasma sciences does for you. Now, we also do a lot of really fun basic research. This is the work these are images from my own laboratory. We're part of an organization called Magnet US, which is a set of facilities around the US that are providing user opportunity for students and researchers to come and use our facilities. Here is just a small list of the users that actually come and do experiments at our facilities. And this is just some of the work from a number of our students. And in particular, this is also images from some of our collaborators. If you're interested in any of the work that we do, this is just a small snapshot of some of the work that has come out from our lab in the last couple of years. And I'll leave you with the fact that these are incredibly rich systems. These are all images from my laboratory, and frankly, these are all from my students. I don't do anything useful anymore, but these are waves, these are filaments, and dust transport. And then this is what Steve and Elon's PhDs are going to be on all of these wonderful dynamic behavior. So with that, let me just conclude. I think plasma physics is this amazing system. It is the intersection of E&M and classical mechanics and statistical mechanics. We embrace some of the greatest scientific challenges, and plasma science and engineering offers solutions to problems that have great economic impact. Everything from plasma medicine to plasma agriculture to microelectronics. And the very last thing is that you can't do this kind of work without a really great team, and in particular, a really great and diverse team of scientists. These are, I'm the PI, these are my research partners, Uwe and Ava, my current set of graduate students, and undergrad, and my recent PhDs. And this was us at a group meeting a couple of weeks ago. This gives you a sense of the team that we've tried to build at my institution. See Elon laughing there. So with that, thank you. Where's Steve? And Steve is out there as well.
Thank you.
Sure.
We're going to wait until the end to take questions, so just in the interest of time. The next gentleman I want to introduce is future Professor Connie Williams at the University of Rochester, actually where I did my first my first postdoc. Connie, actually, I'm on this National Academy study on what's called high energy density science, and this comes under that umbrella. And I was in a meeting and they were talking about all the great work that this guy, Connie Williams, had done. So I'm just, listening. But then I looked on my, on the internet and looked him up and found out he was an African-American. I almost fell out of my chair. And then when I righted myself, he doesn't even have a PhD yet. He's a graduate student and he's doing all this groundbreaking work. So I am very, very proud of what Connie has been doing. Okay, but anyway, he is a PhD student at the University of Rochester. He has a Provost Fellowship, Frank Horton Fellowship, and an HEDP Equity Scholarship. He performs theoretical and computational research in what's called direct drive, and he will explain direct drive to you. Inertial confinement fusion at Rochester's Laboratory of Laser Energetics, and specifically, he designs fusion capsules and laser pulses for experiments on what's called the Omega Laser Facility. He received the American Association of Physics Teachers Outstanding Teaching Assistant Award in 2020. And one really interesting thing that he does shows his social engagement is that he will soon teach mathematics at the Attica Correctional Facility this coming spring. And with that, I will introduce my good friend, Connie Williams.
Thank you, Sakazi. I really appreciate the introduction. I appreciate you reaching out. I was actually wondering how you did find me to ask this up. So we're learning all sorts of things today. So as I said, I'm Connor Alexander Williams. I'm at the University of Rochester. It's an honor today to talk to you about really how the sausage gets made. I'm really excited to be able to share with you the recent advances, not only what they're doing at the National Conditioning Facility, which Ronnie Shepard will talk to you about afterwards, but what's happening in other labs that are looking at different ways to do fusion as well. This has been a really monumental last few years, so it's really exciting to share that with you today. So what I'm showing you here on the title slide is actually a very large achievement that we've just recently done in the last 2 years, which is get hotspot gain, as we call it, which is getting more fusion energy out than we get energy into the hot core, the hot spot of the fusion plasma that we shoot with these laser beams. And to do this on our system, which is 30,000 joules, which is big for everyday life, but is not big in comparison to what is required for ignition. This is a very monumental achievement. And so it's my pleasure to talk to you a bit today about this. So step forward. Okay, awesome. So just to summarize some of these different milestones we've reached recently, we have reached yields of 300 trillion fusion reactions with what is really the crux of my thesis, which is the thin ice DT liner target, which we've designed. And to put that into context, here you're seeing a graph of the neutron yield over time, right? So out here you have 2016, and you have about a 5-year stretch where you sort of plateaued right here at about 150 trillion fusion reactions. And these designs have allowed us to double that almost instantly. So there's still progress being made on old laser systems. They say you can't teach an old dog new tricks, but you can teach a laser new tricks. So we've also been able to, as I said on the title slide, to exceed the amount of energy coupled into the hotspot with our fusion energy with both high convergence ratio targets, right? So ones that we compress quite a bit, and also the liners. And this has been done in part by looking at new avenues in order to continue to get improved performance. So one of those is by doping the targets with silicon. And another is by using our ingenuity with lasers, right? So there's a technique called multi-pulse driver, which has helped us couple more energy to the target. Those in large part have allowed us to reach pressures of almost 80 billion atmospheres, 80 gigabars with the highest hydroscaled Lawson criterion. So I'll talk about the Lawson criterion. It is essentially one number that we use to give an all-encompassing measure of how well the implosion went. And that corresponds to the burning plasma regime, which is a crucial step in getting ignition. Let's move forward. Anyone that's worked in fusion knows that it takes a team, it takes a village, honestly, to make any of this work. And this is my team, this is my village. So I'd be remiss to ignore these folks, and they, everything has to be done, very precisely to make any of this stuff work. So I first wanted to start off with giving a little bit of background for how inertial confinement fusion works. So Ed gave a great definition of magnetic confinement and alluded to, to inertial confinement. I want to focus on how that actually happens, that process. So everything in inertial confinement fusion starts off with a target, which we call, the target capsule. And it consists mainly of 3 different layers. So you have an outer ablator, which is what the laser primarily interacts with at the beginning of the implosion. Below that, you have an icy mixture of deuterium and tritium. So those are the ions that we want to fuse. So you have to first freeze the target to around 17 Kelvin before you can shoot it. And then there's a large gaseous region. So this target is actually very tiny. It's about 1 millimeter in diameter. And these layers, as you can see, are only tens of microns. So it's a very thin shell. And that is what we start off with before we shoot it. We characterize this by laser pulse. So when you go and design an experiment, a designer like myself will have to figure out how you want the laser power to vary in time in order to send a sequence of shocks to very carefully implode the target in the way that you want. And so this is a field with a ton of jargon. So I just want to get that out of the way. So you have these features here, these early spikes, which are called the picket and the laser pulse, in case I allude to that later. As we said, we have the blader on the outside. There are two very, very important parameters which we use in designing a good implosion. And that is the in-flight aspect ratio, which is just simply the ratio of the target's radius to the shell thickness. So which we can track through with the outdoor implosion. And then also the 80 bat. So the 80 bat is just a measure of the entropy, essentially, of the shell as it's in flight. And so one thing to think about is that low entropy allows you to compress more and essentially get more fusion, but high entropy is good for stability. And so there's a trade-off. Everything is about sacrifice in ICF. And there's also the convergence ratio. So just taking the ratio of the initial target radius to whatever the final radius is that you are able to implode it to, and then the definition for aerial density. What I've shown here at the bottom is the Omega laser facility. So this is where we actually perform these at the University of Rochester. It is the fourth most energetic laser in the world. Although the second and third are somewhat, getting up to speed in terms of operation. But this laser is one shot per 45 minutes. It has 60 laser beams that we impinge on the target. And we use a neodymium glass laser whose natural line is in the infrared, but we pass it through frequency conversion crystals to turn it to ultraviolet light. And that's also to couple better to the target. So this is a 30 kilojoule, 30 terawatt behemoth that we unleash a few times a year. So to continue, as Ed mentioned before, we're trying to fuse deuterium and tritium nuclei together in order to get energy out. And then here is the distinction between direct drive and indirect drive. So at Omega, it is the world's preeminent direct drive facility. And that is where you actually are firing the target directly with the laser beams. So there's a direct interaction between the laser and the target, whereas indirect drive, which was famous for the ignition shot in August of 2021, they employ an indirect drive approach where you have what is essentially a gold can, and you shoot the laser beams in the can, heat it up, turn it to an X-ray oven, and you allow the X-rays to drive the target. But what happens basically is with this laser, you heat up the outside very quickly. It causes the outer layer to flay off, and by conservation of momentum, it drives the rest of it in. So we're literally making a spherical rocket with laser beams, which I think is just pretty cool. So the characteristic speeds for this are truly 1,000,000 miles an hour, actually, 400 kilometers a second. My work has been to improve that speed up to 600 kilometers a second to get more yield. And so essentially the stages of the implosion are starting with the target, you send shockwaves through it, you compress the target, and then right when you've compressed it, the gas that's in the center heats up to 100 million degrees, and that's what starts the fusion. And the fusion alpha particles that are produced, as you see here, this alpha particle, you want them to deposit their energy back into the implosion to heat it up to cause the fusion rate to increase. And this is thermonuclear instability that we call ignition. So in general, I'll be talking mainly about two campaigns. We'll focus on the second, but what drives the bus at the facility is the optimization campaign, which is, we know that with a 30 kilojoule laser, you can't ignite a target. It's just too small. It's actually not big enough. In order for that bootstrapping process with the alpha particles depositing their energy back in to happen, you need more aerial density. And so we need to find a way to scale up to larger energies to figure out what would happen on a laser system if it was larger. And so the optimization campaign is focused on improving that number through the Lawson criterion, which I'll give more information on in a second. What I've been focused on is the thin ice DT liner campaign, which is what's the sole purpose of is to just improve the fusion yield. We just need more fusion energy. We need more fusion neutrons. For obvious reasons, that's what the goal is at the end of the day, but also to kick us into a broader parameter space that we can then make sure we're not in a local minimum or in a local maximum, right? And we can actually probe the space to figure out what the best course of action is. And so that allows us to get higher yields. And also it's very important to be able to look and see what type of direct drive approach you could have on the National Ignition Facility before you can make a larger laser in order to do direct drive at the NIF. And so these are a prime candidate for those as well. So when we talk about hydroscaling up to larger energies, we want to think about the pressure that we get on Omega, keeping that constant and just scaling up with size, where the laser energy is proportional to the volume of the target. So just give a quick outline of where we're going. We're going to talk about fusion performance metrics, how we figure out how we're doing, and then go on and give a little aside as a statistical mapping model, which is how we improve, and then go over the recent achievements that we've made with target and laser pulse modifications. So I've mentioned the Lawson criterion. This is sort of the be all end all in terms of figuring out how well your implosion performed. And really, it's a measure of what Ed was talking about in the last talk, which is you need to get enough density, you need to get a high enough temperature, you need to hold it long enough. What's interesting about inertial confinement fusion is that the only thing holding this tiny stars together is its own mass inertia. It wants to explode. It's actually quite literally a tiny bomb. And so what is most different between the way that we go about it and magnetic confinement, such as tokamaks like ITER, is that our densities are much higher. The temperatures are around the same, but the confinement time, whereas they're trying to confine for seconds, we confine for hundreds of picoseconds, right? So we're looking at less than a billionth of a second that we're actually trying to have this fusion take place. And so that is a function of the areal density, the yield, and whatever mass we can assemble on stagnation. And so that number chi is proportional to the pressure and the confinement time. And as we said, we're keeping the pressure constant as we look to scale this theoretically to higher energies. And so that chi scales with size. So at certain points in time, I'll be talking about chi on omega. At other times, I'll be talking about this hydroscaled chi, as we call it. And so one way to think of that is just looking at whatever we get at Rochester, scaling it up by a factor of 4. We're not just concerned with chi. We also want to be able to measure the hotspot pressure and the hotspot energy. Unfortunately, there's no way to, you can't stick a needle in this and figure out the pressure like you would with a basketball. There's no direct measurement that we have. And so we have to infer it from other measurements. So this was what I was focused on mainly over the summer, was to try to find a better model to figure out what's actually happening in these implosions. So models have been used in the past to try and infer pressure. One of the ways that our model differs is, one, allowing the electron temperature and the ion temperature to differ, because we know that those won't actually be equilibrated in this short amount of time. The ions will be hotter. And the other is allowing more information of the shape profiles from simulations, right? So basically the radial profile of the temperature, the radial profile of the density are basically taken from simulations. And then we figure out what the central values are, what the actual shape of this is, or what the actual values are from constraining it through this yield formula. So basically the yield depends on your species fractions, so how many deuterons you have, how many tritons you have, how long it burns, which we get from neutron diagnostics, the ion temperature, which we also get from neutron diagnostics from looking at the width of the energy spectrum of the neutrons, and all those together, then we can figure out what the pressure is, and also the volume, which we get from X-rays. So the model has been basically based off of being able to apply this formula to simulations and figure out, can they infer the right answer? So what you're seeing here is basically LILAC is our one-dimensional radiation hydrodynamics code that we use at Omega. And so on that implosion in the simulation, the pressure. And what we've done is try to figure out, using this method of inferring the pressure, do you get the right answer? As you can see, everything is pretty much right on the line. So when we apply this model to experiments, we expect to get the right answer. Moving on to the statistical mapping model, this is the primary way that we're able to figure out what is degrading our implosions and therefore get better. So statistical mapping of experimental data onto the simulations is how we are able to isolate physical dependencies. So as I said, there's a lot of jargon in ICF. One of the terms that we use is the yield over clean, the YOC, which is basically just the yield that you get in the actual experiment divided by what you get in the simulation. And that is broken up into a series of degradation terms that all have their own physical backing. So I want to step through just 4 of these terms and then talk about 2 in particular that we decided to start tweaking in order to figure out where to go. So the first is this beam term. So as I said, Ronnie will talk about indirect drive, where a more or less isotropic bath of X-rays is used to implode the target. We have a finite number of beams, and those beams have a beam spot that is non-uniform. And so when they land on the target, you have hot spots and cold spots. You have some areas, as you here with the illumination pattern, that are really intense and others that are less so. And that is going to imprint, that's going to drive instabilities in the target. You also have this laser imprinting, which is the very first interaction of the beam with the target. The beamlets of the laser beam itself, of each individual beam, are going to also imprint seeds on the target. There's also defects in the actual capsule, and that is a source of degradation. And the dependencies of these are isolated as well. So for the YOC beam, this is a ratio dependent on the ratio of the beam radius to the target radius. And for the short wavelength instability, You see that is dependent on the alpha, so the adiabat, as we said before, the entropy, and the in-flight aspect ratio. And then you have this L equals 1 term. So if you've ever held a water balloon and squeezed on one side, you see how it flows out. We get the same thing in these implosions. So if you shoot too hard on one side, you'll cause it to squeeze out. And so that is something that also will degrade the pressure and the yield on these shots. And then we have a Yacht helium-3 term, which is basically comes from the fact that tritium is slightly radioactive. It has a half-life of 12 years, which you might not think would be important, but there's such a small amount of mass in the gaseous region of the target that as it starts to decay from the ice, it can build the pressure up very quickly inside that region and cause you to not be able to compress as much. These last 2 terms, we don't focus on so much because we handle them on every shot. The way to handle Yacht helium-3 is just to shoot quicker. So you fill the target and you shoot it after 3 days instead of we used to wait weeks and months. And then for this L equals 1, we are now able to, from the neutron spectrum that we get, to figure out an offset. You can figure out the Doppler shift and figure out the flow, and then you just literally just move the target 1 or 2 or 10 microns over, and you can eliminate this. But these last 2, these are the bane of my existence. Awesome. So I'm going to step through a little bit quicker. So basically, what we're seeing here is the degradation from these terms specifically. And so moving to the left is giving you greater coupling. Moving to the right is giving you greater uniformity. And for the liner campaign to get more yield, we want to sell out for all the one-dimensional aspects. So we want to get greater coupling, even if it is at the cost of stability. And over on the right with the short wavelength, actually all of our implosions stay in this sort of middle region right here, like 1.5. And so that's where we want to operate. Moving on, this is really how we've been able to improve these implosions, which is to figure out what does the fusion yield depend on, and then how to move in this parameter space. So the fusion yield is proportional to the energy you can get into the hotspot and that loss in parameter chi. And so that hotspot energy, we want to look at where does it come from. So it starts in a series of transfer steps. So you start off with the laser energy. The laser energy is transferred. Some of it is absorbed by the target. Some of that energy ends up as kinetic energy of the shell as it implodes. And then some of that kinetic energy ends up in the hotspot. And so just to step through, I don't think I have time to get through really all these. One way that we've been able to improve the laser energy is just to change this aspect of the laser called smoothing by spectral dispersion from off to on, or from on to off, which gives us higher conversion. And it gives us a few more kilojoules of laser energy. In order to absorb more, you want bigger targets. You want to dope it with silicon, so the silicon gets higher collision absorption, and that is going to also improve the absorption. You also have this hydrodynamic efficiency term, which basically if you go to thinner targets, so higher in-flight aspect ratios, you're going to get more conversion because it acts as one piston stopping all at one time. And so that is actually how we're going to start focusing on each of these. So for the liners, we want to maximize the hotspot energy. I'll move through there. That slide is just telling us that using 1D simulations, we'd expect to be able to reach hotspot gain above 1. What I'm showing here is that theory actually has been matched in experiment, which is that when you dope it with silicon, you actually do get more absorption. And using this MPD, this smoothing by spectral dispersion on and off, you get the beam to shrink, and that also couples more energy to the target. And that A/B comparison of silicon versus no silicon, you can see that the yield jumps up 25%. The hard X-ray signature, so the 2 plasma decay instability, which tends to thwart all of our implosions, gets dropped down to 1/4 of its former value, and you absorb more. This is really the crux of the issue, though, with how we're going to get higher yields, which is these thin ice DT liners that I've been focusing on. By going to very thin ice layers, we're able to push the implosion velocity up from 450 kilometers a second up to 600. And this is how you're getting these very, very high temperatures and to get large yields. And you can see the difference in the laser pulse that we're using with this. So more or less, it's just a much more aggressive pulse. You need to shorten it. You need to hit it much harder at the beginning in order to stabilize it. And so that is sort of the leap of faith that we've been able to take recently to be able to make sure that we can make these targets survive. And so all of this, the most important of those terms that I showed earlier is this transfer term, that we're able to couple more energy to the hotspot from getting the kinetic energy of the shell into the hotspot. So thinner capsules, which we've started to employ, allows us to get this eta hotspot, this conversion efficiency much, much higher. So that you see these liners now are coupling over 50%. And this is really the crux of the issue. This is the money plot, which is that all of these together have allowed us to get more fusion energy out. Then we've been able to couple into the hotspot, which is a crucial step in looking to the future of fusion energy. And we've done it with only 30 kilojoules of energy. So this parameter you'd expect to scale with size. And so we're actually losing at these lower laser energies. And it'd be much better if we're able to shoot with 2 megajoules. And we also don't have help from alpha heating. So all of this together really is how we're able to get the records that we've been able to lately, to get these doubling in yields. And it's why there is a lot of excitement in not only the indirect drive world, but also the direct drive world. So thank you for your time.
Thank you for that excellent presentation. So finally, we have Dr. Ronnie Shepard from Livermore. Dr. Shepard received bachelor's, master's, PhD from the University of Michigan, which is one of the top nuclear engineering departments in the country. His research in plasma physics grew from his interest in understanding the physics of stellar interiors. The focus of his thesis work was, in fact, on transport properties in strongly coupled plasmas, a condition that dominates white dwarfs. He joined the Atomic and Plasma Physics Group at Livermore, pursuing the study of high energy density plasmas using short and long pulse laser matter interactions. Currently, he's the scientific leader of the short pulse laser opacity work at Lawrence Livermore and director of outreach at Livermore's High Energy Density Sciences Center. He's the chair of a group called LaserNet, and LaserNet is a consortium of high-power laser facilities in the US and Canada. And Ronnie was recently elected as a fellow of the APS. And without further ado, turn it over to you. Are you okay? I'm not okay. We're having a little bit of a technical problem here. Okay, well, while you are working on that, why don't we bring the other 2 speakers out and we can just answer questions while you Okay, any questions that you've heard so far about what you've heard so far?
We got some technical difficulties.
that he's having?
Okay, so I've got a quick question for Dr. Tanner.
Oh,
You
slideshow
talked
is on
about,
slideshow.
Okay,
well, I'm sorry, the last speaker. What was your name?
Her doctor, I should
Yeah.
say that. Oh, no, you want to give
All right, so when you were talking about increasing the firing rate from a few weeks to, we'll shorten it to 3 days. What is puzzling me there is it seems to me that you're adiabatic in terms of the environment in a lot less than 3 days. So why are you waiting so long?
Oh, okay. There we go.
So really, the firing rate there, also I want to make sure I'm clear, is the time after we fill the target with the deuterium and the tritium versus when we shoot it. So totally separate from the laser itself. During that process, there's a layering that needs to happen. So what happens is you start off with the empty shell and you diffusion fill it. So you slowly ramp up the pressure of a gaseous mixture up to like 1,000 atmospheres, and that will diffuse through, and then you flash freeze it. And that allows you to make an ice layer, and it starts off from like one nucleation site and then closes in on itself. But that layering needs to happen a few times. So they'll normally like melt that again and do it again in order to make that smooth, because if the ice roughness is too large, it'll destroy you. And so basically you can't do too short because we don't have enough people for that, and going too long, you'll get killed from the helium. I don't know if that answers the question, but yeah, appreciate it. It's all good.
So
Yep.
we're ready to go, so I'll turn it over.
Let's see, is this working? All right, well, I'll just change it manually. So yeah, I've been sent out here to talk about the shot that was kind of heard around the world in 210808. For those of you that are familiar with laser plasma interactions or ICF, they know about that, but I suppose some of you won't know anything about it. So I'll tell you a little about this. So there's a huge team of people working on this. Livermore is kind of become the hub, but there are people working on it all over the world. CEA is in France, AWE is in England, and you can see there are lots of people from private institutions, from public universities, lots of people working on it and have contributed significantly. So I thought I'd sort of tell this like a story, because ICF kind of reads like a thriller. And as any book should start with an introduction, it sort of began with the understanding that you could get energy from the strong nuclear force. When you force particles together, there was an energy deficit, and that equals MC squared gets turned into energy from that energy deficit. We kind of learned how to exploit that, but only in an uncontrolled fashion. And we learned how to do that real well. But I think Connor talked about this and Ed talked about this. In order to do this in a controlled fashion, you really need to satisfy this condition called the Lawson criteria, where this N is a density, that tau is a confinement time, and that value has to be on the order of 10 to the 20 seconds per meter cubed. And the details of how that's calculated, I hope they talked about, but if you have questions about it, I'd be happy to tell you or talk to you about it. Nature does this naturally with gravity as well, as you know, by the sun and the stars. It confines things by pulling everything in and holds it there for a long, long time until you more than satisfy this criteria. ICF tries to emulate that, but with lasers. And I think Connor talked about that, where you take a shell of material, you fill that shell with deuterium, tritium gas, you heat the shell, it explodes off, it creates an opposite reaction. They call it the rocket effect. It compresses the gas to fusion temperatures. So the first chapter of this is just a little bit of history. The paper that this all originated from was written by John Knuckles in 1972. The authors in that paper said that with about a kilojoule size laser, you could make this work, which, by today's standards, that's a tiny laser. As a result of that, there was sort of an international effort. People scrambled around the world to do this because as has been pointed out, it essentially results in an infinite source of energy because, you could just take water and get deuterium from it, and there's a lot of water. So, but, every story kind of has a villain. And in this case, I won't talk about this in too much detail because I have less time than I thought. But if you look at this, this is sort of the shell that you try to heat with the laser. At the first interaction, you generate these plasma waves. Those plasma waves scatter off, the laser scatters off those plasma waves and results in laser light that doesn't get into the target, that's wasted. Some of that gets in though. The next layer, you generate these filamentations. Filamentations is another source of loss of energy, not really heating the target efficiently. You go in further, you lose energy by this method called cross beam transfer, and that's because you have multiple beams heating the surface. And this was an interesting observation, was that laser energy coming in from one direction can leak out the path of a laser beam coming in an opposite direction or in another direction. It's called cross beam transfer. So that became another energy loss mechanism. And as you go in further, you generate another source of plasma waves to plasmon decay. Those plasma waves also provide a method of scatter. You can scatter off those plasma waves and that laser light doesn't get into the plasma. One of those plasma waves or those plasma waves can decay by emitting a hot electron. That hot electron, you might think that's great because that's energy into the plasma, but it ends up preceding the heating from the laser and it ends up preheating the gas, which makes it harder to compress. So none of that stuff is good. And the result of that sort of meant that you really couldn't do this with a kilojoule sized laser. You needed a lot more. The good thing was that they also discovered was all these instabilities sort of scaled as 1/λ, which is why even direct drive, they use as short a wavelength as possible. But it turns out there was another method of doing this. Once again, I think Connor spoke to this and Ed did as well, and that's indirect drive, and that's making the wavelength, that heating wavelength, extremely short. The way indirect drive works is you take multiple beams, you send those beams into what's called a holorum, which German for can or cavity or empty room or something like that. And the laser beams heat the walls to high temperatures, generating X-rays. Those X-rays then heat the capsule wall, and that capsule then explodes. It launches a compression into the gas compresses, and then you get fusion. So being from Livermore, I'm obligated to talk about this. This is what NIF looks like. It is the world's highest energy laser. Can't say the most powerful, but highest energy laser. It's about the size of 3 football fields. So this is big science at the extreme. To give you some scale, this is what the target chamber looks like. It's like 10 meters in size. That holorum that the laser beams focus into is like a centimeter in size. The capsule that the X-rays from the walls heat are about 2 millimeters in size. And ultimately, the implosion, the hotspot, is only about the size of half size of a human hair, half the size of a human hair. So the scaling, oh, what's that? Clickers what? Oh, I can do this? You sure? No, it doesn't do anything. See, I'm doing it. Oh, wait a minute. Oh, there we go. All right, astrophysicists, you're right. Okay, so how does this work? I'm also obligated to show this because, everybody who talks about NIF has to show this. You call for a shot to the control room. Shot director then does a countdown. I guess you can't hear it. Okay, anyway, shot director calls for the shot. The capacitor banks are charged, and then there's a, wait a minute, that wasn't supposed to happen. Hang on. There we go. Oh, wait a minute. Okay. Let's see if this works. Yeah, here we go. Okay. Shot director calls for the shot. Shot director does a countdown. Okay, he's counting down. Then, right, capacitor banks charge. Then in the control room, nanojoule size laser pulse is released. And that pulse gets split and sent into 2 parallel amplifier chains. And you can see those beams bouncing back and forth. Each time they bounce back and forth, they gain more and more energy. So it bounces back and forth. When you see it neck down, it's going through what's called a spatial filter. And that's to throw away some spatial frequencies that aren't contributing to the focus, which ultimately can damage the optics. So they spatially filter the beam. You continue to amplify, and let's see, continue to amplify. You notice the beams are all red. Eventually, the beams go into what's called a switch yard. They get redirected. Yeah, redirected. And then, even though you're going to heat with X-rays, you still frequency convert the light. You can see it goes from green to blue, and then the light goes into the holorum. And then the holorum walls are heated. Usually it's gold. The gold starts to emit X-rays. You can see there's billionths of a second. The X-rays then heat the shell. The shell explodes, creates a compression, and you get fusion. All right. Okay, so all that works. Where's my Mr. Fusion at? Okay, the answer is slow down. Okay, if you want to try and understand why you don't have a Mr. Fusion yet, you got to move to the next chapter. And that's the look at the goes ins and the goes outs. The goes ins and goes outs. If you look at the energy conservation, the time dependent heat balance, this is the energy that goes in, the time dependent temperature, that's the specific heat of the deuterium and the tritium. This is all in the hot spot. This is a term which is heating due to the alphas. So if you've successfully done this, you're adding more heat to the plasma or to the hot spot from the alphas. But then you have these loss terms. This is loss due to radiation. It's radiating a bunch of the energy away. This is loss due to heat conduction. And then this term is negative, but it's tricky because this is what we call PDV work. That's the shell, after the shell has blown away, this is the work being done on the gas, compressing it. Well, that looks negative, but it turns out it's actually positive because this dV, dt is negative. So this is initially a positive term that's adding to this. No, that doesn't matter. Okay, so the way this works is during the implosion phase, the radius is getting smaller. These terms are contributing. This term and this term is contributing to the heating. Then you read stagnation, okay? At stagnation, you no longer have this term contributing, it's now hurting you. It's taking energy away. It's expanding and taking energy away. So to get this whole thing to work, you really got to you have to get to the point where this term is actually dominating and dominates well before, in terms of time, before this term has a chance to take over. These other terms, 5 minutes. I'll go faster. Okay, faster. Okay, so if you look at the window of time that you integrate over, this term, as I said, has to be bigger than this term before stagnation. This MNV is the minimum volume that you achieve. If you can do that successfully, the plasma will burn. Okay, and that's kind of what I just said. One of the things that they found in both as a result of simulations and measurements was that the time-dependent temperatures has to scale at a rate of T to the 3.6 in order to get this to work. Okay, I'm not going to talk about this. There's no time. Okay, chapter 3 is the evolution. And okay, so if you look at how things have evolved in the ICF community, 2011 is when NIF was opened. And the first experiments, the yield was 2.5, I'm sorry, on this axis is the yield, and this is year. In 2011, the first shots yielded had 2.5 kilojoules of energy of yield. The plasmas were unstable, and LPI, which is these laser plasma instabilities, they were still a problem, even though you were in the X-ray regime. This is an X-ray, this is an image, neutron image, I think, no, X-ray image of the compressed plasma. So it was asymmetric, it's highly asymmetric. If you really want to emulate how nature does this, this thing has to look very, very symmetric because a star is very symmetric. So if you move forward, this information was used to improve on things dramatically. You can see the yield went from 2.5 kilojoules to 25 kilojoules. And the way that was done was by reshaping the laser pulse that was driving the X-rays. That improves the stability and it increased the velocity of the implosion. Okay, so that was actually an order of magnitude. That was actually a pretty big jump, but you can see you're nowhere near what the input energy of the laser was, which was 1.8 megajoules. Further improvements came when they managed to reduce the LPI by reducing what's called the fill tube. And the fill tube is a tube that goes into the spherical shell. It fills the deuterium gas in the shell right before the shot. But one of the things they didn't realize, because you can't put everything in simulations, was that fill tube actually drove instabilities as well. So that fill tube was causing these things to look asymmetric. They reduced the size of it and that improved it dramatically. The other thing is they noticed was the shell material itself, which in the past had been CH. By making it harder, the ablator actually improved the symmetry and had additional improvement to the symmetry, and they made that out of diamond. Okay, so, but you're still at 55 kilojoules. You're nowhere near what the laser input energy is. Now, this looks insignificant, right? 55 kilojoules, 55 kilojoules. They redesigned the holorum itself to try and get more energy in by changing what's called a laser entrance hole. And that's the hole that the laser beams come in. And you say, well, why does that matter? Well, it turns out as the laser beams go in, it's blowing off material also. And so by blowing off material, eventually you reach the critical density at the entrance hole and then no more energy gets in. So they redesigned it and they found that they could get the same amount of energy with less drive, which was, like I said, 55 kilojoules, but it turns out that 55 kilojoules was with less drive energy. And you can see now it's starting to look kind of symmetric. Okay. Oh yeah, I'm rushing. Okay, I'll get through it. I'll get to it. There's only a few more view graphs. Okay, so after redesigning the entrance hole, they redesigned the holorum itself a little bit, and it further increased it by roughly a factor of 3. You can see the symmetry is getting better. And then this happened. Yeah, we were all stunned by this. Like, it happened on a weekend, and we all got this, the physicists at the laboratory got this emergency email for a WebEx. And we're all like, what's going on? What's going on? We get on the WebEx and then they show us this and we're stunned. They were stunned. The people who did the experiment were stunned. No one expected this. Okay, this was an order of magnitude increase. And now you can see the yield is 1.35 megajoules. The laser input energy for this was like 1.7 megajoules. So you can see you are now real close to break even, which has been a goal from day one. Okay, they took the shot, it blew out all the lights in the facility. It saturated all the detectors. They didn't even have the detectors to measure it at the time. Okay, so I'm being told to hurry up, so I'm gonna hurry up. Okay, there's been shots done post then. You can see some of these, the initial early shots right after that was less than a megajoule. That was by design. We're trying to understand the mechanisms that led to the 1 megajoule shot or 1.3 megajoule shot. They've since done, I'm not going to talk about it, but they've since done shots which are comparable, 1.3, 1.2 megajoules. I actually had a view graph in here on that, but I pulled it out. Those shots were discussed at the last APS meeting. So what we found out was that, yeah, I mean, you can do ICF, but it's a lot harder than we suspected. From the beginning of the story, it was like 1 kilojoule will make this work. 1 kilojoule will not make this work, ever, okay? It takes a lot of design work to make this happen. We know it works and works all the time if you do it in Nevada. In a hole in Nevada, it works and it works beautifully. If you can overdrive the capsule, it will work. The trick is to getting it where you're right on the hairy edge. You're not really overdriving it and still get it to work. And so what's going on now? Okay, I'm not going to talk about this. There are improvements that are being made, further improvements that are being made to the holorum. They believe they can get more energy out. They want to eventually get a refurbished version of NIF, which will put out even more energy because they're so close to the threshold to make this, to make it work. You're on an exponential curve, and so small changes make a big difference. And with that, yes, okay. there are heroes in this story, and these are the heroes. These three are particularly important heroes. Andy Kircher designed the upgraded holorum. Alex Zystra performed the experiment, and Omar Hurricane was the one who truly realized the systematic steps that you really needed to do to get this to work. And with that, I guess I'll take questions.
What we're gonna do is to ask each of the speakers to come out, and we can only ask one question. So if there's anybody have a burning question, I don't think we need the chairs as it turns out, because, thank you for that. Is there a burning question? Yes, gentleman right here, yeah.
Hello, my name is Alamayu. I'm a grad student at UCSD. I guess my question was for Connor. Since you said that the laser energy at Omega isn't high enough to produce ignition, are there plans to go to NIF to replicate the shots that you did at Omega? And like, are there modifications that you need to make
Yeah,
if you
so
have to do that?
great question. So I'll say sort of two things on the note. One is, that was sort of actually another one of, I didn't really have time to sort of get into the specifics of why, but that's one of the things that the liners also introduce is, because the NIF is a polar direct drive setup, you can actually shoot it directly, but you'd rather have it be symmetric, right? So you do polar direct drive. That obviously has to be very robust against instabilities because you're shooting along the poles. These types of targets seem like they'd be very scalable to actually shoot polar direct drive on the NIF and actually be a reason to believe you're able to get like 800,000 joules of fusion energy out in a very consistent manner on that, very repeatable. The other thing is we're looking to do Omega next. So we're always looking to like improve the actual facility. We're trying to figure out right now what energy that would be, 100 kilojoules, 200 kilojoules. It'd be a broadband laser. So you get rid of all laser plasma instabilities that thwart us now. And could you, show burning plasmas, potentially ignite maybe with a better drive rate, like 300 kilojoules. All that is sort of in the works right now. But the reason why we do experiments, why Omega still exists, is that's the workhorse of the HEDP community. And figuring out, before you can go build another facility, you have to figure out how it scales, right? So do the experiments at our scale, right? And figure out what you actually need at those larger scales. So I don't know if that answers the question, but that's, yeah. Awesome.
Okay, let me just ask Ronnie if he could say a couple of words about student internship possibilities.
Sure, we love students. No, we don't eat them, but we love having students. So to be fully transparent, this is not my work. My work is really studying sort of the plasmas that occur inside of here. Because as Dr. Sakazi has said, my interest was in stellar interiors. This is exciting for someone like me as well, though, because the one thing we haven't really been able to do reliably is make burning plasmas. And this is now a burning plasma, which is a stellar interior. So yeah, we love students. I've had a student working for me for the past 25 years. Not the same student, but I've had a student getting a PhD with me for the past 25 years. They've cycled in and out. And I currently have an HBCU student at FAMU who's hopefully going to be finishing in the next few months. So both the ICF program and where I sit, the physics program, we love having students come to the lab. And if any of you are interested, I'm happy to take your information because, as I said, as my side job, I'm also part of the outreach program for the Center of High Energy. I'm the director of outreach for the Center of High Energy Density Sciences. So, yes.
Okay, so if they had to say a couple of words.
Right. Okay. In terms of student programs, I mentioned in my talk, our facility, we are a DOE collaborative user facility, a collaborative research facility, not technically user facility. And so right now, if you actually come to our website, and you can always come find me, we're actually running the competition right now for runtime on our various facilities. And folks are welcome. This is not only students, but also researchers that may be interested in doing experiments either in plasma physics, or actually our real resource is this 4 Tesla class magnet with a removable bore. So we can, anything that can fit within a 0.5 meter diameter that you want to do explorations up to 4 Tesla magnetic field, just let me know and we can accommodate those kinds of experiments. And we've done diagnostic testing for everything from basic plasma experiments to fusion diagnostics at our facility.
Okay, and finally, Connor wants to say a couple of words.
Yeah, so if you're an undergraduate right now, if you want to apply, we have RUs at Rochester. In your application, make sure that you make it known you want to be at the Laboratory for Laser Energetics. There's a lot of people doing a lot of great work. One of the things that also makes the laboratory unique is that, as you see, grad students are designing shots, right? It's the only place you can do that in the world. So make sure that you apply. And shameless plug for me, if anyone is giving out jobs, I should be graduating in a year, so talk to me afterwards. Thank you.
Thank you so much. Yeah, this is so exciting. I wish I could do it, but I'm old. So I enjoy what you guys are doing, but definitely speak to these three gentlemen. It's exciting. When I was a student, like a couple of years ago, when I was a student 50 years ago, you know, it seemed like it was so far in the future, but now it's on the verge now. So definitely, if you're interested, get into this. This will make a big difference in the energy supply. Okay, thank you.
2 years ago, it seemed like it was so far in the future.
All right. Thanks, guys. Yeah, appreciate it.
Yeah, oh yeah.